Welcome to this deep dive. Our mission today is going through our stack of notes on, well, how scientists actually map the human brain. We're going on quite a journey, looking at four distinct tools researchers use to peek inside the black box, from tracking real-time electrical signals as they fire, all the way to examining a famous brain that was literally sliced into over 2,400 pieces.
And it really is a black box. What stands out in these sources is that scientists are constantly playing this game of trade-offs. They're almost always having to sacrifice space for time, or vice versa, just to get a glimpse of what's happening in our heads.
Yeah, you see that immediately with functional MRI. Since we already know fMRI builds a moving 3D map by, tracking oxygenated blood, the real focus in the research is what you can actually do with that map.
The spatial accuracy is just incredible. I mean, we're talking about pinpointing brain activity down to maybe 1 or 2 millimeters.
Wow, literally that precise.
Oh, absolutely. And it has massive real-world applications. For instance, the data shows that people dealing with depression often have increased activity in emotional centers like the amygdala,
Right.
while simultaneously showing reduced activity in cognitive control areas, like the hippocampus.
Here's where it gets really interesting, though. For all that millimeter precision, fMRI has a pretty glaring blind spot. Because it relies on tracking blood flow, there is a 1 to 4 second time delay before the scanner detects anything.
Wait, I know 4 seconds might not sound like a lot to a casual observer, but in brain time,
Yeah.
that is an absolute eternity.
Exactly. Neurons fire in milliseconds. By the time the blood flow catches up, the thought or impulse is long gone. Plus, as our sources point out, fMRI is purely correlational. It shows us what areas light up together, but it can't definitively prove cause and effect.
Because of that 4-second delay, researchers who need speed have to abandon fMRI entirely and look at electrical data instead.
Right, which means using an EEG. They stick between 22 and 34 electrodes directly on your scalp to track the amplitude and frequency of your brain waves in real time. Looking at our notes here, it's wild to think that researchers Dement and Kleitman actually used this exact method way back in 1957 to identify REM sleep.
It's a classic tool for a reason. And from EEG, we get ERPs, or event-related potentials. This is where researchers take that real-time electrical data and use statistical averaging to filter out all the random background noise.
So they're isolating the brain's exact reaction to a specific prompt.
Precisely. You get a millisecond accurate response to a specific task, like a language or attention prompt. There's a catch. Because the electrodes sit right on the scalp, they simply can't access deeper brain structures. They only scratch the surface.
So if we take a step back, if fMRI is too slow and EEG is strictly surface level, how do researchers ever get a truly detailed look at the physical architecture of those deep brain areas?
Historically, they wait until the person is deceased. Post-mortem examinations.
Ugh, the old school approach. This is how we learned about Broca's area from the patient known as Tan. And there's that incredible detail in our research about the famous patient AIM. His brain was literally sliced into over 2,400 pieces after he died, just to definitively prove the hippocampus's role in memory. Just picture having to slice an organ 2,400 times.
It's intense, but it's a foundational method. Studying a brain post-mortem provides highly detailed, conclusive structural diagnoses. We still rely on it to confirm conditions like Alzheimer's disease. But it completely lacks what researchers call ecological validity.
Basically, you're looking at the hardware of a computer after the power has been unplugged.
Exactly. The software, the actual active mind is gone.
So what does this all mean? For you, the listener, it means that the next time you read a catchy neuroscience headline claiming scientists have found the brain area for something, you should always ask how they measured it, because no single tool gives us the full picture.
Absolutely not.
The fMRI is incredibly detailed but slow. The EEG is lightning fast but only reads the surface. And postmortems are brilliant for structure, but they're posthumous.
It raises an important question to leave you with. If our current tools either have a massive time delay, only read the surface of the scalp, or require the subject to be, well, deceased, what profound split-second mental processes are we entirely blind to right now, simply because our technology hasn't caught up?